Welcome guys to my channel. In this video I'm going to show you how to calculate deflection and angle of deflection of a loaded beam. This is the beam that we have and it has this side view and it's 3 meters long and all other parameters are given there. So what I was saying, basically what we're trying to say by the deflection, this is the deflection that I want to calculate. When a beam is loaded at the end, it will deform and deflect in this manner. Okay, so finally the beam will look like this. So I want to calculate by how much does it deflect, how much did it deflect from here to here. Okay, that is the deflection I want to calculate. So for us to come up with that deflection for this example, we've got a UDL and a point load. Due to the uniformly distributed load, it will deform, and also due to the point load, it will deform, that is, it will deflect. Okay, so for us now to come up with the maximum deflection of the beam, we're going to say the deflection due to the uniformly distributed load and the deflection due to the point load. Okay, you have to know these formulas, and this E is the modulus of elasticity and I is Ixx, moment of inertia. Okay, so as you can see, we can actually work this out. So y maximum, that is the deflection, will be equal to, as you can see, this W is there for uniformly distributed load, and you know that for uniformly distributed load it must be kilonewtons per meter. Okay, the units for its per meter. So for us now to have weight per meter for the uniformly distributed load, we say it's 150 kilonewtons. Okay, and we vary by 3 meters for it to be per meter. We got 3 meters and it's 150 kilonewton. So it's 150 kilonewton divided by 3 for us to have the load per meter. Okay, so if say 15 divided by 3 is 5, so get 50,000 Newton per meter. Okay, so we're going to substitute for this equation now. So it's W 50 kilonewton. Okay, and L, the length is 3 meters, so it's 3 power 4. Okay, and divide by 8, and to 8 for the point load. W for the point load, what is it? It's 60 kilonewton, so it is 60 kilonewton, and length 3 meters, so it's 3 to the power 3. Okay, all over 3, and we're going to multiply it by 1 over EI. E is the modulus of elasticity, and this is the moment of inertia. Okay, so what I'm going to do now, we don't have I, we're going to solve for I, but we know that this face, we've got the solid part, and then this space here, this void. What we're going to do, we have these two rectangles. We actually know that for Ixx, for solid, rectangular or squares, it will be Ixx is 1 over 12 bd cubed, where b is the base, d is the height, and this is the formula. So without wasting time, we actually know that we've got two rectangles, so we're going to subtract the Ixx for the solid part, and subtract for this empty space here. Okay, so it will be 1 over 12 bd cubed for the solid part, and subtract 1 over 12 bd cubed for the void, like this. Okay, so as you can see, we've got a common base there. Okay, so what the base for the solid part is 0.16, and what is the height for the solid? 0.26 cubed, and we're going to subtract For this one, the base for that one, the small rectangle is 0.11, 0.11, and the height 0.21, 0.21 cubed. Okay, all over 12. So if we punch these figures in a calculator, we have something like 0.000149. Okay, so this is the value for ixx. So we're going to substitute it in our question here. So it will be 50 times 10 to the power 3 over 8, 3 to the power 4 there, and we're going to add this one of 60 times 10 to the power 3, and we're going to multiply by 3 to the power 3 over 3. Okay, and 1 over E. Well, we've been given the value of E, the 200 gigapascals. So it's 200 times 10 to the power 9. Okay, and we're going to multiply by our I. That is our I. 0.0001149. Okay, so we're going to use our calculator. Punch this long thing. Okay, okay, so if you punch these figures in the calculator, we get something like 0.035002408 meters. Okay, so if we're going to simplify it, it will be 0.035 meters. So this is the deflection for this material. So if you can see that if this is the original beam, it will deflect by 0.035 meters. So that means from here to here it will be 0. The formula that we are going to use to calculate for the angle of deflection, that is theta max. So WL cubed, this is for the uniformly distributed load, and this is for the point load. So let's solve it out. It will be equal to, for the uniformly distributed load, it's 50 kilonewtons. Okay, and going to multiply by length is 3 squared, 3 cubed over 6. We are going to add it for the point load is 60 kilonewtons, and the length squared is 3. Going to divide by 2, and I'm going to multiply rest with 1 over. We now have the value of E is 200 gigapascals, and multiply by ixx. Okay, so ixx, we've calculated ixx, so I'm going to substitute it into this long equation, which will be equal to 50,000 times 3 cubed all over 6, and I'm going to add 60 kilonewtons. 3 squared is 9, all over 2. Going to multiply by 1 over 200 times 10 to the power 9, and our x 0.000149.5. Okay, we're going to use our calculator for this one. Okay, so if you punch this in the calculator, okay, something like 0 1 6 5 6 0 2 7 9. Okay, so if you're going to round now, it will be 0.0166 radians. Okay, so this is how calculate for the angle of deflection for that beam. So as you can see, you have to know these equations. You actually need to know them and understand them. In this video, I'm not going to show how to drive them, but you have to know them. Thank you for watching. If this video has been useful to you, don't forget to subscribe to my channel, hit that notification bell so that don't miss any new videos coming into my channel, and also don't forget to leave a comment. Thank you for watching. Till next time, bye bye.